So exponential growth and decay. And this, like I said, it's not brand new to you. You've done these, you've used these exact same formulas actually before, but we're just going to look at them again. So exponential growth occurs when a quantity exponentially increases over time. Okay, so we're looking at, for our little parent function, graph-wise, it would look something like this. That would be your exponential growth, right? So one way to write an exponential growth function would be f of t, t being time, equals a, which is your initial amount, times 1 plus the rate of increase to the t power. And t is the time unit that you're using within whatever it is you're doing at that time. And we'll look at that as we go through some of these. Okay, so a is the initial amount, r is the growth or decay rate as a decimal, t is the length of time. All right, so exponential decay occurs when a quantity exponentially decreases. So parent function wise would look like this. So the only difference would be it's still f of t equals a times 1 minus r to the t power. So sometimes you will see this written as just 1 and it would say f of t equals a times 1 plus or minus r to the t power. It's the same thing, it's just saying you have to decide if you're going to add or subtract. Okay. Now, wording in questions is important. You're expected to read directions and read all the words in a question, right? So this says, Brooke started her career with an annual salary of $64,000. Well, it should be $64,000. I didn't catch that. Each year thereafter, her salary is increased by 2.5%. Write and use an exponential growth function to find her salary when she retires after 30 years. So write and use, that means we have to write a function that isn't us just substituting everything in, okay? And this is increasing, so it'll be exponential growth. So it'll be a function of time equals her annual salary, which is $64,000, times 1 plus the rate. So her rate is 2.5%. What does that look like as a decimal? 0.025. Good. Make sure you can change that correctly. To the t power. So that's us writing the equation. So now writing the function. So really we can find her salary at any point because this is the function that I'm going to use. So I wrote it, now I'm going to use it, and I double check that my time is in years because it says this happens first of all each year, and I want to know what happens after 30 years. So I'm just looking for f of 30, that equals 64,000 times, and then you could, since you're going to use a calculator, you could leave it like this if this was like difficult, but it's actually going to be easier if you just put 1.025 to the 30th power. Okay, does that make sense to you? We good? Okay, so go ahead and type that in. The other nice thing about these calculators is you can literally put it in just like this with parentheses, don't even have to use the time sign, you know, whatever works for you. And we're going to get, I'll type this in too. So 64,000 close my parentheses, to the 30th power. So one thing on on these online calculators, like I haven't even hit equals or anything, but like if I just backspaced one and it hadn't typed in 30 yet, I just had 3, well, that's what it is to the 3rd power, and it kind of gives you your answer as you go along. But if you need to redo and like maybe I needed it at 30 years and 25 years and 20 years, then I could just, here's my 30 answer, and then I could type in my 20 answer, and then and I wouldn't have to redo it. So either, oops, or I can hit enter and then it'll stay there. Okay, we good? Now, when we do stuff, because I know this is an on-level class, but it's still getting you on the track to calculus and AP calculus, and because y'all could definitely go to AP calculus next year. everything has to be accurate to 3 decimal places unless you're told otherwise or unless it doesn't make sense for the situation we're in. We're talking money, so does 3 decimal places make sense? No. So, and then we have to round correctly, right? So this would round to how many cents? 33, yes. So our answer then is, and you got to use units, so that's your money, right? $134,244.33. We good with that? Questions? All right. Let's look at the next one. So it says, Kate drank an energy beverage with 150 milligrams of caffeine. Each hour, the amount of caffeine in her system decreases by about 12%. Again, write and use, and it kind of gives it away. It says an exponential decay function. It should just say a function. Exponential decay function to find the amount of caffeine in her system 1 day later. Okay, so my units of time don't match. There's hours and days. So you just have to make a decision. Would it be easier to do the whole thing in hours or easier to do the whole thing in days? I'm thinking in hours, right? So we're going to put like T equals hours. So F of T equals my initial amount, which is 150, times 1, then what do? Plus or minus? Minus, because it's decreasing. 1 minus, what's 12% as a decimal? 0.12, yeah, 0.12, to the T power. Okay. So T is in hours. I want to know what happens 1 day later. How many hours is that? 24. F of 24 equals 150 times. Now, if you don't want to have to think about this, you can just leave this so you don't do anything weird. 1 minus 0.12 and put it in the calculator just like that, and you'll be fine. It's 0.88 if you wanted to do that. But there's no reason to like figure that out and then do it. You can just let the calculator do it all at once. Okay? So go ahead and type that in, and let's see what we get. All right. Leo, what'd you get? Okay, we're going to do 3 decimal places unless we're told otherwise or it's money. You got it. So it's 6.977, and what would my units be on this? Milligrams, yeah. Okay, questions about that? We good? All right, so let's talk half-life. Y'all remember chemistry? All right, so half-life. It says the half-life of mercury 197. Now, does that 197 going to be a number in my actual calculations? No, because it's the name of things, so don't do weird stuff. Is 3 days. Write and use an exponential decay function to find the amount of mercury 197 left from a 50-gram sample after 20 days. Okay, so what do we think our time? I've got 3 days and 20 days, so I'm thinking T is going to represent days. Would you agree with that? So I'm going to have F of T equals, my initial amount is how much? My initial amount of mercury. 50 grams, yeah. So it's going to be 50 times 1, and this is decaying, so it's 1 minus, what's the rate?
3.
You want to use that 3 in there. What's the rate? What does it say? Half-life. What does half-life mean? 0.5, right? Half-life is when it is half as much as it was before, right? So it's decaying by 50% or by 0.5, so it's 1 minus 0.5 to the T, but it's not just the T power. Okay, so it's T we're going to put up there, but we're taught T is the amount of days. Does it decay by 50% every single day? No. How many days does it take? 3. So we'd have to take the total amount of days and divide it by 3, because since it happens every third day, right? So your actual equation is going to be t over 3. Okay, does that make sense to you? All right, so then it's 20 days, so I'm going to do f of 20. That's equal to 50 times, well, 1 minus 0.5 is just 0.5 to the 20 over 3 power. Now, when you get to the exponent in this calculator, like you push the little exponent button so it shoots you up there, then push the fraction button and put 20 over 3. Okay, and it makes everything look real nice. Let me see, I think I can do that on here too. Oh, I don't think I have a fraction button on here. I guess not. I think there is one on the Delta Math one apparently. Either way, once I'm in there, I can do 20 divided by 3. Oh my gosh. It automatically makes it into 1. Okay, right? Now what we got there? Do I agree with that? Okay, so that gives me, so what would I write down, Jose? 0.492, good, and what are my units? Grams. Okay, everybody okay with that? So that's your exponential growth in day, oh my God, growth in decay, based on how if something happens every day or every hour or whatever. Okay, we good? We're going to look at a different kind here. So we also have what's called continuous growth and decay. If you see the word continuous or continuously, something to that effect in there, that means you're using this formula, which uses E. Okay, E is a constant. It's 2.7. You've heard it before. 2.718 blah blah blah. How have you heard? What have you heard E used with? Do you remember? Huh? Okay. Yes, yeah, exactly. Thank you. You were paying attention yesterday. That's right. Remember I told you about 2.7, and so it's exponential growth and decay again, but it's continuous. All right, and so the formula is a little different. Well, it's a lot different. I'm going to show you a little 4-minute video, I think it is. I just realized I messed something up when I started this recording, so it's going to mess that up. But I'm going to show you a little 4-minute video, and then that explains E a little bit better than I will by myself.
We've made a video about pi, the ratio of a circle's circumference to its diameter. But there's a less famous, but equally fundamental number known to anyone who's taken high school algebra. It's about 2.718281828459045, and so on. And it was first defined by Jacob Bernoulli, but later Leonhard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So if you stick $1 into a bank account with 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So, while E may not be as famous as pi, it's easily as fundamental and immensely important.
The number pi.
Okay, so that kind of gives you a, how do I get out of this? A little bit of an understanding of E. And so I was looking for something that was simple that would kind of show you where the number even comes from. But if you see how if you compound it more and more and more to where it's continuously and you can't even count how often it's happening, you are approaching E. And so that's why, because you can't always judge things by every, like a salary increase, boom, it happens right then, it happens right then. But other things that fade away, like if ice is melting, it's not like every 5 minutes there's just less and there's less, like it's continuously melting, right? So there has to be some way to identify that stuff. So sometimes the quantity is consistently increasing or decreasing at an exponential rate and not just after each year, month, day, hour, etc. The formula to the right, okay, so this is called your Pert formula. A equals capital P for principal. It's the same thing as A was on the other one. It's your initial amount. Times E to the RT power. And even though we need to know that E is about 2.7, that's not anything we're ever going to type in. We would use the E button when we do things, okay? So there's your Pert formula. So this says a garbage dumpster started with 4 pounds of garbage. The amount of garbage increased continuously. So that right there is your little siren that says, I'm going to use the Pert formula. By 35% each day from this point forward. Because it's not like you're only allowed to throw something in the dumpster every hour, right? People would just be throwing stuff in there all day. Find the amount of garbage in the dumpster after 2 weeks. So we're going to write and use the formula again. So I have A equals, my initial amount is 4 times E, my rate is 0.35 times T. And in this case, my T, let's see, it says each day, and it says 2 weeks. So do we want our time to be days or weeks, you think? Days, yeah. I think that would be a little bit easier to think about, right? So then A equals 4 times E to the 0.35 times what? 14. And then your E button on the calculator, it is on the far right-hand side. It's in yellow, so you have to hit the shift button and then natural log, and you'll get the little E to pop up, okay? Daniel, tell me what you got. Daniel, you were playing with the calculators when you came in. You hadn't even typed it in yet? No. $537.159. Good. 0.159. What are my units? Pounds. Very good. That's a lot of trash. We good? All right. So the next one says the population of a town is declining, so it's not increasing, it's declining at a continuous rate. So again, ding, 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 we're using the Pert formula, of 25.9% every 2 decades. If the current population is 16,000 people, find the population in 8 years. All right, so I know it's going to be the Pert formula. One thing it says up here, because I can't subtract, like on the front, if it was growth, I added. If it was decay, I subtracted. But this says R is positive, positive for growth, and negative for decay. So the rate's the same, we just make it negative, okay? So I'm going to have A equals P, which is my initial amount, 16,000, times E to the negative 0.259, since it's decreasing, times T. Now, I'm talking decades and years. I got to pick one. Which one's going to be easier to use overall? Years. Okay, we can do years. Okay, so we've got, I think of it in terms of decades, but we could do years. I think if you think about, I mean, we could do years if you want to do years, it's fine. Okay, so if T is, because how many years are in a decade? 10, right? 10 in a decade, and this isn't even a full decade, so if we talk about things in years, well, we could use 20, I mean, it's fine. I would use decades. It's just me. I would do decades. So T is, let's do decades, so we don't get it all messed up. Okay. Then if it's happening every 2 decades, I only have 8 of those decades, or 8 of those years. It'd be 8 out of how many years? 20. So as long as you make that 8 out of 20, it really doesn't matter. So A equals 16,000 times e to the negative 0.259 times 8 over 20. And Adrian, what'd you get? Oh my goodness.
I get 14,425.37.
Okay, so let's talk about decimals here. Just like with money, we had to be careful with decimals, okay? And I asked him what he got, so it was fine. He gave me the right answer. But can I have part of a person? No. So we'll go with just the whole number there. 14,425 people. Okay, we good? What questions we got? All right. All right, so we're going to look at logistic growth. I'm not going to give you any questions like this, and you're not going to be tested over it, but I think it's a good thing to look at, especially if you're going to calculus, you'll see it. Plus, it kind of makes some of the exponential stuff that we talk about maybe make a little bit more sense, because this is really kind of what you're going to. So I'm just going to do one question and just talk about what all this means. So it says, sometimes a quantity exponentially increases, but then levels out, approaching a horizontal asymptote called the logistic growth model. So here's an exponential increase, but then it's going to kind of reach a limit. Like it's not going to get any higher than that. Just like this eventually is going to have to, I mean, I doubt there's going to be like 10 people, then 2 people, then 1. I mean, it's probably going to kind of level out maybe there too. And this is going to be super easy to do because basically we don't understand enough about it that it has to give us this, and it pretty much plugged everything in for us. So the math is not going to be difficult, but I want to talk about why this would make sense. So it says a disease begins to spread in a town of 20,000 people. After T days, the number of people who have been infected by the disease is modeled by the function below. And I used this question long before COVID, but there's a pretty good COVID type of thing too. Infected by the disease is modeled by the function below. Using the function, find the number of people infected after 10 days. Okay, so why do you think that this would be a logistic growth and it wouldn't just look like our plain old exponential? If we're talking how many people, this is time and then how many people are infected. Because there's only a certain amount of people. Like how many people are infected can't exceed 20,000 because that's how many people there are. Does that make sense to you? So that's why sometimes this itself doesn't make sense. Okay, so we have this, and then we're going to put in, so I'm going to find f of this, and this does say after t days, and this is 10 days. So we're just going to do f of 10 equals, so it's going to be 20,000 in the numerator, which is our limit basically. 1 plus 1150 e, and you don't worry about what the other numbers mean. That's a whole logistic thing that we are definitely not getting into. Negative 0.95 times 10. So go ahead and put this in there. Use the fraction button first. Hit the fraction button, put 20,000 in the numerator, arrow down to the bottom, and then get that typed in. And if you plan on going into business, there is such a thing called business calculus. Logistic growth is definitely a business type of thing. Obviously, it's applicable to a lot of other things, but. All right, so did you get 18,414 people? That's a little scary, isn't it? in 10 days. It's almost everybody, but it's not everybody. We'd be up here and we'd be getting closer and closer and closer to that 20,000, but you know, maybe they're immune or something. Okay, we good on that? It is very scary. Okie dokie.